Tonight, as you lie in the quiet familiarity of your room, you may not realize that just a few days ago, 4 human beings entered a silence that no one on Earth could reach. For nearly 40 minutes, as the Orion spacecraft of Artemis II moved behind the moon, every signal disappeared. No voices, no data, no way to know if they were still okay. This was not a malfunction. This is how the universe works. On the far side of the moon, there are no relay satellites, no protective magnetosphere, and nothing standing between human life and deep space. Artemis II returned safely in April 2026, but what it brought back was not just an achievement. It was a question about limits, about isolation, and about where humans truly belong in this universe. If journeys like this make you think, take a moment to like the video and subscribe to Space Lull so we can continue exploring the things most people never stop to notice. Now, let your mind slow down and step into that silence. In April 2026, when Artemis II left Earth, it was not just another rocket launch. It marked the first time in over half a century that humans returned to lunar orbit with an actual crew. From Florida, the Space Launch System carried the Orion capsule off the pad, passing through the atmosphere within minutes before gradually entering low Earth orbit. From a technical standpoint, none of these steps were unfamiliar. We have done this hundreds of times. But this mission did not end there. After completing its initial orbital adjustments, Orion entered the most critical phase of the journey, translunar injection. A precisely timed engine burn pushed the spacecraft beyond Earth's direct influence and set it on a trajectory toward the moon, approximately 384,000 kilometers away. From that moment on, the spacecraft was no longer in a familiar environment. It was entering a region where even small errors could become significant problems. Over the following days, Orion traveled through deep space at tens of thousands of kilometers per hour. Navigation systems continuously refined its trajectory. The crew carried out routine checks. Everything unfolded in an environment where there was no external support beyond the spacecraft itself. As Orion approached the moon, its speed and trajectory were calculated to perform a far-side lunar flyby. This was not a stable orbit, but a path designed to use the moon's gravity to bend the trajectory and send the spacecraft back toward Earth. It is a technique first used during the Apollo missions, but one that still requires extremely high precision. And then, that moment arrived. As Orion began to move behind the moon, the far side, all communication systems with Earth disappeared. Not weakened, not distorted, but completely gone. Mission Control in Houston no longer received any signal from the spacecraft. No life support data, no images, no audio. There was no way to confirm the condition of the 4 people on board. This period lasted for nearly 40 minutes. Technically, it is called loss of signal, LOS. But the term sounds far less significant than the reality. Because during that time, Earth-based monitoring systems became effectively meaningless. What was happening inside the spacecraft, no one knew. The reason for this silence was not a technological failure. It was rooted in the structure of the moon itself and the limits of physics. The moon does not have a network of satellites like Earth. As Orion moved behind it, the moon's massive body, over 3,400 kilometers in diameter, became a perfect barrier to all radio signals. Radio waves cannot pass through solid matter at that scale, and without a relay system on the far side, the signal simply had no path. This meant that, for those 40 minutes, Orion was completely isolated from Earth. Not in an emotional sense, but in a physical one. If any issue had occurred during that time, whether minor or critical, the crew would have had to handle it entirely on their own, without any support from the ground. No guidance, no real-time analysis from hundreds of engineers, no external backup. Only the crew and the systems they carried with them. This was not a new phenomenon. During the Apollo missions, especially Apollo 8, 10, and 11, astronauts experienced similar blackouts while passing behind the moon. Communication losses typically lasted between 30 and 45 minutes, depending on the trajectory. And in each case, mission control could do nothing but wait. But there is an important difference. In the 1960s, losing communication was accepted as an unavoidable part of the mission. Technology simply did not allow for anything better. Today, we live in a world where constant connectivity is the norm. Satellites cover Earth's orbit. Internet connections are continuous. Real-time communication is expected, not exceptional. And for that reason, the silence of Artemis II feels different. Not because it is more dangerous than Apollo, but because it reminds us that some limits have not changed. No matter how advanced our technology becomes, we still cannot cover all of space. There are still regions that humans must enter without connection, without guarantees, without real-time control. During those 40 minutes, Orion was not part of a larger system. It was an independent entity. Inside, the crew continued working. They monitored systems, checked parameters, ensured the trajectory remained correct. Everything proceeded as planned. But what made that moment significant was not what happened, but what did not. No communication, no confirmation, no one observing them in real time. And then, as the spacecraft gradually moved out from behind the moon, the signal began to return. First, data, then voices, and finally, confirmation that everything was still nominal. For mission control, it was a moment of relief. For observers, it was a sign that the mission remained on track. But on a deeper level, that moment carries a different meaning. It shows that even though we can calculate trajectories down to the meter, control temperatures to precise limits, and monitor thousands of parameters in real time, there are still periods when humans must accept not knowing. And that is not a flaw that needs to be fixed. It is a limit that needs to be understood. During those 40 minutes, what truly happened inside the spacecraft? The answer does not lie in any unusual event. It lies in the silence itself. A silence not caused by a lack of technology, but by the nature of the universe. And perhaps that is the most important thing to understand. When Orion moves behind the moon, the first thing to understand is that this region is not the dark side in terms of light. The correct term is the far side, the part of the moon that always faces away from Earth due to tidal locking. This means that from Earth, we only ever see about 59% of the moon's surface, while the rest remains almost entirely hidden from direct view. However, what makes this region unique is not about light, but about isolation from human communication systems. Unlike Earth, where thousands of satellites form a continuous network, the moon has no such infrastructure. As Orion moves behind it, there is no longer any direct line of communication between the spacecraft and ground stations. There are no relay satellites positioned to transmit signals. As a result, this creates a region of space that is, from a communication standpoint, effectively cut off from the rest of humanity. From a physics perspective, this is a straightforward phenomenon. Radio waves travel in straight lines and cannot pass through a large solid body like the moon. With a diameter of over 3,400 kilometers and a dense silicate structure, the moon acts as a perfect shield. When Orion is behind it, all signals from the spacecraft are blocked, and at the same time, signals from Earth cannot reach the spacecraft. This creates what is known in engineering as a radio shadow. And it is through this shadow that Artemis II passes. From a technical standpoint, this is not unexpected. The trajectory is calculated in advance, the duration of signal loss is predicted with high accuracy, and the crew is trained to operate independently during this period. But from a human perspective, the experience is very different. Throughout the earlier phases of the mission, even at distances of hundreds of thousands of kilometers, the crew maintained continuous communication with Earth. The signal delay, roughly 1.2 to 1.3 seconds, introduced a slight pause in conversation, but remained within normal communication limits. They could speak with mission control, receive instructions, transmit data, and know that someone on the other end was always monitoring. But once they enter the far side, that connection disappears. Not weakened, but completely gone. There is no fallback, no backup channel, no secondary layer of communication. During that time, Orion is no longer part of a global communication system. It becomes an isolated unit, operating entirely based on its onboard systems, the crew's training, and the decisions they make in real time. Another important aspect of the far side is its physical environment. The terrain differs significantly from the near side of the Moon. While the near side contains many maria, large basalt plains formed by ancient volcanic activity, the far side has a much higher density of impact craters. The surface is rougher, less uniform, and reflects light differently. This does not directly affect Artemis II, since it is a flyby mission, but it highlights that this region is less familiar and less thoroughly studied compared to the side facing Earth. Historically, humans have only observed the far side directly during a limited number of missions. Apollo 8 in 1968 was the first time astronauts saw this region with their own eyes. Subsequent Apollo missions and a number of robotic probes added to that knowledge, but overall, it remains one of the least familiar areas in near-Earth space. In that sense, Artemis II represents a return of humans to that region after more than 50 years. But the difference is not in the act itself. The difference is in the context. Today, humans are accustomed to constant connectivity. Nearly everything can be monitored, recorded, and transmitted in real time. Even complex missions aboard the International Space Station are continuously observed, with telemetry systems sending thousands of data points every second. Any anomaly can be detected almost immediately. The far side of the Moon is one of the few places where that model no longer applies. In that region, for a certain period of time, there is no real-time data. No one standing behind to verify. No parallel system analyzing and issuing warnings. Only the spacecraft and the people inside it. This leads to an important question. If we are preparing for missions farther away, such as Mars, where communication delays can reach up to 20 minutes, then what Artemis II experiences on the far side is not an exception. It is a smaller version of what will become normal in the future. In other words, that silence is not a rare anomaly. It is an inevitable part of moving away from Earth. And seen from that perspective, the far side of the Moon is not just a geographic region. It is a boundary between a world where humans can control almost everything and a world where we must accept that there will be periods when we do not know what is happening. And it is across that boundary that Artemis II passes, not to discover something mysterious, but to confirm something we have long understood, yet rarely confront directly, that there are places in the universe where silence is not unusual. It is the default state. When Orion moves behind the Moon, the change is not limited to the loss of communication with Earth. The physical environment surrounding the spacecraft also changes in a way that cannot be directly observed, yet has a measurable impact on both the human body and onboard systems. On Earth, we live within a natural protective layer that most people never think about, the magnetosphere. This is the region of space around our planet where Earth's magnetic field deflects high-energy particles from the Sun and deep space. Most harmful radiation is either redirected or trapped before it reaches the surface. Even the International Space Station, despite being outside the atmosphere, still operates largely within the magnetosphere. This means astronauts on the ISS receive a certain level of protection. Their radiation exposure is higher than on Earth, but it remains within controlled limits. Artemis II is different. As Orion leaves low Earth orbit and moves into deep space, it gradually exits the effective protection of the magnetosphere. By the time it reaches the far side of the Moon, the spacecraft is almost fully exposed to the radiation environment of space. There are two primary sources of radiation in this region. The first comes from high-energy particles emitted by the Sun, commonly referred to as solar particle events. These consist mainly of protons and electrons accelerated during solar eruptions. Under normal conditions, their intensity fluctuates and can be partially predicted. However, during strong events, radiation levels can increase rapidly and reach dangerous thresholds in a short period of time. The second source is galactic cosmic rays. These are extremely high-energy particles originating from outside the solar system, often associated with phenomena such as supernova explosions. Unlike solar radiation, these particles carry higher energy and are significantly more difficult to shield against. They can penetrate materials and cause damage at the cellular level. In the environment of Artemis II, both of these radiation sources are present. Data from previous missions and measurements taken on board Orion indicate that radiation levels in deep space are significantly higher than those in low Earth orbit. In some estimates, a single day outside the magnetosphere can be equivalent to several weeks or even months of radiation exposure on Earth, depending on solar activity at the time. What matters here is not the exact number, but the nature of the environment. Radiation in space is not something that can be seen or directly felt. It has no color, no sound, no immediate sign that it is increasing or decreasing. Yet it continuously interacts with matter, including the human body. The systems on board Orion are designed to mitigate these effects. The capsule's structure, combined with the internal arrangement of equipment, provides a certain level of shielding. More sensitive areas receive additional protection. The crew is also trained to use designated storm shelter zones in the event of a strong solar radiation event. However, it is important to understand that these measures do not eliminate radiation entirely. They only reduce exposure to levels considered acceptable for a short-duration mission. Artemis II lasts approximately 10 days. Over that period, the total radiation dose received by the crew remains within NASA's safety limits for human spaceflight. But if this duration were extended to months or years, as in missions to Mars, the problem would become far more significant. This is why the environment that Artemis II travels through is considered a critical test. It is not just a journey to and from the Moon. It is an opportunity to measure, record, and better understand radiation exposure in deep space under real conditions, with humans on board. One notable observation is that during the mission, recorded radiation levels were at times higher than initial predictions. This does not necessarily indicate immediate danger, but it does highlight that the space environment still contains variables that are not fully controlled. During the period when Orion is behind the Moon, with no communication to Earth, there are also no real-time alerts from solar monitoring systems in Earth orbit. If a major radiation event were to occur at that moment, the crew would have to detect and respond based solely on onboard sensors. This brings us back to a central theme of the entire mission: independence. Not only in navigation or system operation, but in dealing with the surrounding environment. Radiation is not a threat in the sense of a sudden failure or collision. It is a background condition, always present, always active, and cumulative over time. Because of this, it is often less noticeable, even though its long-term effects can be significant. As Orion moves through the far side of the Moon, the crew cannot see radiation. They cannot hear it, but they know it is there, as an inseparable part of the environment they are passing through. This does not make the mission immediately dangerous, but it reinforces an important reality. Space is not empty in a safe sense. It is an environment with physical conditions very different from those humans are adapted to. And to exist within it, we must bring everything we need: air, temperature control, pressure, and protection from things we cannot see. And among all of those factors, radiation remains one of the few that we have not fully mastered. Not because we do not understand it, but because we do not yet have a way to eliminate it completely. And during the time Orion passes behind the Moon, that reality does not change. When discussing Artemis II, most attention is often directed outward, toward the trajectory, the Moon, the distance, and the events unfolding in space. But throughout the mission, there is a simple reality that is often overlooked. Everything related to the crew's survival takes place within a very small volume, entirely controlled by human design. The Orion capsule is not a spacecraft in the way we might typically imagine. It is not spacious, it does not offer much room for movement, and it is not designed for comfort. The habitable volume for the crew is approximately 9 cubic meters. With 4 people inside, the effective space per person is extremely limited. Every movement must be considered, and every piece of equipment is arranged to maximize the use of each centimeter. Inside Orion, all conditions necessary for life must be created and continuously maintained. Air pressure is kept at levels comparable to those on Earth. Oxygen and carbon dioxide levels are controlled through filtration and recycling systems. Temperature is stabilized between 20 and 24 degrees Celsius, despite the extreme thermal variations the spacecraft experiences when passing through sunlight and shadow in space. The life support system on Orion operates as a closed loop. Air is circulated through filters to remove CO2. Moisture is collected and processed. Water is stored and used under strict control. All of this is designed to minimize the need for external resupply, because in the environment where Artemis II operates, there is no possibility of direct support from Earth. One important distinction is that, unlike the International Space Station, which can receive regular resupply missions and consists of multiple connected modules, Orion is a completely independent system for the duration of the mission. Once it leaves Earth orbit, there is no way to send additional resources, no way to perform major repairs from outside, and no rapid evacuation option in the event of a critical failure. This requires all onboard systems to operate with a very high level of reliability. At the same time, it also means that the crew must understand these systems in detail. They are not only operators, but also observers, diagnosticians, and, in some cases, the ones responsible for resolving issues directly. During the period when Orion moves behind the Moon and loses communication with Earth, this role becomes even more evident. There is no longer a mission control team monitoring every parameter in real time. No group of engineers analyzing incoming data and providing recommendations. What remains are the displays inside the cabin, automated alerts, and the experience of the crew. If a parameter deviates from its normal range, they must assess its significance on their own. If a system responds slower than expected, they must decide whether to intervene. And if multiple signals appear simultaneously, they must prioritize actions based on their training. All of this takes place within an enclosed space where sound behaves differently. Because of the proximity of surfaces, noises are more noticeable. The hum of ventilation systems, the flow of pumps, the operation of electronic equipment, all of these create a continuous background sound. It is not complete silence in the physical sense, but rather a form of isolated silence where no external sound exists. No wind, no natural ambient noise, no indication that an external environment is present. This creates a clear distinction between the inside and the outside of the spacecraft. Inside, everything is controlled and maintained within predictable limits. Outside, physical laws still operate, but they are not adjusted to suit human needs. This contrast is one of the defining characteristics of deep space missions. Humans do not biologically adapt to space. Instead, we carry a small portion of Earth with us, in the form of technology, and maintain it within conditions where it does not naturally belong. Orion, in this sense, is not just a vehicle. It is an artificial living environment designed to function for a limited duration. And when the spacecraft moves behind the Moon, that environment becomes the entire world of the crew, not metaphorically, but literally. Everything beyond the structure of Orion no longer has direct interaction with them. There is no reflected light from Earth, no radio communication, no immediate external input. Everything they can observe and control exists within the spacecraft itself. This highlights another key aspect of missions like Artemis II: total dependence on the system. On Earth, if a system fails, there are often multiple layers of redundancy: infrastructure, people, and the natural environment itself. In Orion, those layers exist, but all within the same confined space. If a problem affects multiple systems at once, the range of available options can quickly become limited. For this reason, Orion is not only designed to work well, but also to fail safely. Systems are built with fault tolerance, safety modes, and the ability to maintain minimal operation in the event of a malfunction. But regardless of how well a system is designed, there remains one factor that cannot be completely eliminated: the limitation of a closed environment. Throughout the mission, the crew cannot simply step outside in the usual sense. Extravehicular activities are carefully planned and are not part of Artemis II. This means that the entire experience of the crew is confined to a fixed space with conditions that do not change significantly over time. For a mission lasting around 10 days, this may not present a major issue, but for longer missions, such as future journeys to Mars, this same model would need to be sustained for months or even years. In that sense, Artemis II is not just a lunar flyby. It is a test of whether humans can maintain a stable, closed, and controlled living environment, while being completely separated from Earth's natural ecosystem. And during the time the spacecraft moves behind the Moon, when there is no communication with the outside, the answer to that test is not found in what we hear from mission control. It is found in what happens inside a space only a few meters wide, yet responsible for sustaining 4 human lives, in an environment that does not allow for life to exist on its own. In human spaceflight, there is a concept that every astronaut must understand before leaving Earth. It is not a malfunction, not a technical failure, but a phase that is fully anticipated, yet cannot be eliminated. It is called blackout. In Artemis II, blackout does not occur just once. It happens at 2 different moments, for 2 completely different reasons. One occurs when the spacecraft moves behind the Moon, and another during its return to Earth at extremely high speed. Both share a common outcome. For a certain period of time, no signal can enter or leave the spacecraft. From Earth's perspective, blackout appears as a gap in data. Displays stop updating in real time. Audio transmission is cut off. What remains is the pre-calculated trajectory and the assumption that everything is proceeding as planned. But inside Orion, blackout is not an absence. It is a phase in which the entire system must operate without external support. To understand this more clearly, it is necessary to distinguish between the 2 types of blackout experienced during Artemis II. The first is geometric blackout, when the spacecraft moves behind the Moon. The cause is purely physical. The Moon lies between Orion and Earth, blocking all radio transmissions. There is no way to bypass this without a relay satellite positioned on the far side, and no such system is used in this mission. The second is plasma blackout, which occurs during atmospheric reentry. As Orion re-enters Earth's atmosphere at approximately 25,000 miles per hour, the air in front of the spacecraft is compressed to the point of ionization, forming a plasma layer around the capsule. This plasma absorbs and reflects radio waves, interrupting all communication for several minutes. These 2 types of blackout have different causes, but they produce the same result: complete silence. The key point is that blackout is not a sign of failure. It is part of the mission design. Orion's systems are built to continue functioning normally during communication loss, and the crew is trained to operate independently without relying on instructions from Earth during these periods. However, that does not make blackout any less significant. During the time Orion is behind the Moon, the spacecraft is still traveling at very high speed, following a precisely calculated trajectory. Any deviation, even a small one, could affect the entire mission. But without real-time data transmission, all adjustments must be based entirely on onboard systems. Orion's navigation computers rely on multiple data sources: inertial sensors, star tracking, and relative position measurements. These systems allow the spacecraft to determine its position and velocity without direct reference to Earth. Under normal conditions, this data is transmitted back to mission control for verification. During blackout, that verification does not exist. This does not mean the system becomes less accurate. It simply means there is no second layer of confirmation. Another important factor is the human element. Throughout the mission, the crew follows a structured schedule of work and rest. But during critical phases, such as lunar flyby and reentry, they must operate at a high level of focus. Blackout often coincides with these moments, when reliance on onboard systems and human decision-making reaches its peak. Inside the cabin, displays continue to show data. Warning systems remain active, but the difference is that there is no one on the other end to confirm that the information is correct. No voice from Houston to say everything is within limits. No additional analysis from external experts. There is only the data, and how the crew interprets it. This places a very high demand on training. Astronauts must not only know how to operate systems, but also understand them deeply enough to distinguish between normal behavior and early signs of potential problems. Historically, blackout has contributed to increased tension in missions. During Apollo flights, every time a spacecraft passed behind the moon, mission control had to wait without updates. The return of signal was always a critical moment. Artemis II follows the same principle, but within a different context. Today, continuous data flow is the norm. Even the most complex systems operate with multiple layers of monitoring and analysis running in parallel. Blackout is one of the few situations where that model does not apply. During that time, the mission does not pause. It continues with all its variables and technical requirements. But Earth's ability to observe it in real time is completely interrupted. This leads to a simple but important reality. There are phases in space missions when humans must accept not knowing what is happening in real time. Not because of a lack of technology, but because of the limits of the environment. Blackout does not last long compared to the total mission duration, but its importance is not defined by its length. It is defined by its meaning. It is the point at which every system, every procedure, and every assumption must be trusted without immediate confirmation. And from that perspective, blackout is not just a technical phenomenon. It is a test of the system, a test of the crew, and to some extent, a test of how we understand control. Because during those minutes, no one knows exactly what is happening, and the mission must continue. In discussions about Artemis II, most attention is typically directed toward physical factors such as trajectory, temperature, and radiation. However, there is another aspect that is less frequently addressed yet plays a critical role in deep space missions: the psychological state of humans when separated from their familiar environment for an extended period of time. Inside Orion, the crew is not only dealing with technical demands, but also adapting to a living condition that is fundamentally different from anything on Earth. Limited space, an unclear day-night cycle, and complete dependence on onboard systems are all factors that have been studied for many years. However, the phase when the spacecraft moves behind the moon, combined with the loss of communication, creates a more distinct condition. Under normal circumstances, even in isolated environments, humans maintain a sense of connection with the outside world. A conversation, a signal, or simply knowing that someone is monitoring and ready to respond. All of these contribute to a stable psychological baseline. During blackout, that baseline is no longer present. This does not mean the crew enters a state of panic. On the contrary, they are trained to operate under such conditions. But the difference lies in how the brain processes the environment when there is no external feedback. Within a closed system like Orion, all incoming information comes from within the spacecraft itself. Displays, warning signals, and operational indicators become the primary sources of awareness. As long as these systems function normally, the sense of control is maintained. However, in the absence of communication with Earth, without independent verification from an external source, the brain must rely entirely on what it can directly observe. This increases focus, but at the same time, it raises cognitive load. One important factor is the perception of time. In space, the day-night cycle does not follow the same pattern as on Earth. The crew relies on clocks and scheduled routines to maintain their biological rhythm. But during critical phases, such as the far side flyby, time is experienced differently. Not because it physically moves faster or slower, but because there are no external reference points. No familiar light from Earth. No continuous signal marking progression. Only a predefined duration, and the expectation of its end. In space psychology research, this phenomenon is described as temporal isolation. When external references are removed, the perception of time becomes entirely internal. This does not necessarily create problems over short durations, but it changes how the environment is experienced. Another factor is sound. As mentioned earlier, Orion is not completely silent. Mechanical and electronic systems generate a constant background noise. However, This sound is stable and does not vary significantly over time. This differs from Earth, where sound environments are more dynamic and often originate from natural sources. In the absence of external sounds and without variation in the acoustic environment, the brain gradually shifts toward focusing on finer details. Small changes in system noise, subtle vibrations within the cabin, or alert signals become more noticeable. This can be beneficial for early detection of technical issues, but it also increases the sensitivity of the nervous system to the environment. In this context, the role of training becomes clear. The Artemis II crew is not only trained in technical procedures, but also in maintaining psychological stability under isolated conditions. Simulation scenarios on Earth include extended periods of communication loss, where the crew must continue operating without any feedback from mission control. The goal of this training is not to eliminate stress entirely, but to ensure that the crew can maintain accurate decision-making under stress. During the time Orion passes behind the Moon, these skills are applied directly. There is no external intervention, no adjustments from mission control, only established procedures and the crew's ability to follow them. This leads to an important conclusion. In deep space missions, technology can provide a controlled environment and support system operations, but the human element remains essential. Not because technology is insufficient, but because there are situations where interpreting data and making decisions requires human experience and judgment. As Orion moves through a region without communication, the system continues to operate as designed. But ensuring that everything is proceeding as expected depends on whether the crew can correctly interpret and respond to the information available. This is not an unusual situation. It is part of the mission design. And more broadly, it reflects how humans approach space exploration. We do not only send machines farther, we also carry our own ability to adapt. During periods without communication, when there is no one on the other side, the stability of the mission does not depend solely on the system. It depends on how humans operate within that system. And that is a factor that cannot be fully measured by data, yet it is always present in every mission. As Orion leaves the far side of the Moon and begins to move back into a region where communication with Earth is possible, an important change occurs, not only technically, but also in how the crew perceives their surroundings. During the time on the far side, almost all familiar reference points disappeared. Earth was no longer visible. There was no communication signal. There were no visual cues indicating their position relative to the planet they had departed from. But as Orion continues along its trajectory and gradually emerges from behind the Moon, Earth begins to reappear in the windows of the capsule. This phenomenon is often referred to as Earthrise, the Earth appearing above the lunar horizon. From a physical perspective, this is not a rare event. It is a direct result of the spacecraft's trajectory and the relative positions of the Moon and Earth. But from an experiential standpoint, it carries a different significance. At a distance of nearly 400,000 kilometers, Earth no longer dominates the sky as it does when viewed from the surface. It appears as a small disk with an angular diameter of about 2 degrees, larger than the Moon as seen from Earth, yet still small enough for the entire planet to fit within a single field of view. Features such as oceans, cloud systems, and land masses can still be distinguished, but they no longer appear in a familiar way. What stands out is the contrast between Earth and the surrounding environment. In deep space, the background is almost entirely black. There is no atmospheric scattering of light, no blue sky, no gradual color changes throughout the day. Within this context, Earth becomes a clearly defined object, with its characteristic blue color and white cloud patterns. From a technical perspective, seeing Earth again also means that communication systems begin to function once more. Radio signals can travel directly between Orion and ground stations. Data transmission resumes. Audio communication is restored. System parameters can be verified and confirmed from both sides. But for the crew, this transition is not only about systems coming back online. During the period of lost communication, Orion functioned as an independent system. Every decision, every evaluation was based solely on onboard data. When Earth reappears, it brings with it reconnection to a larger system, a network of monitoring, support, and analysis. This reduces operational pressure to a certain extent, not because anything on board has changed, but because an additional layer of external verification becomes available. Looking more broadly, however, the reappearance of Earth also provides an important visual reference. In space, position is not determined by familiar landmarks as it is on Earth. Navigation systems rely on star tracking, inertial sensors, and mathematical calculations to determine trajectory. But for humans, seeing a familiar object can help reinforce a sense of orientation and direction. In this context, Earth is not just the origin and destination. It becomes a visual reference point that helps the crew understand their relationship to the surrounding space. Another notable aspect is Earth's size and brightness at that distance. Due to its atmosphere and reflective surface, Earth appears significantly brighter than the Moon. This brightness comes not only from reflected sunlight, but also from atmospheric scattering. As a result, Earth becomes one of the most recognizable objects in the crew's field of view as they return from the far side. From a mission standpoint, re-establishing communication and confirming position are critical steps in preparing for the next phase, returning to Earth. Trajectory data, velocity, and system status are re-evaluated to ensure that the spacecraft is in the correct condition for upcoming maneuvers. But beyond the technical factors, there is another aspect that is more difficult to quantify. In reports from Apollo missions, many astronauts described the moment of seeing Earth from deep space as an experience that changed how they perceived the planet. Not because they discovered something new scientifically, but because everything was placed into a different context. From that distance, Earth is no longer a vast environment divided into regions. It becomes a unified system, containing all the conditions necessary for life within a finite space. Artemis II is not the first mission to provide this perspective, but it is the first time in decades that humans have experienced it directly in a modern context. And this creates a clear contrast. While Orion must carry all life support systems within a space only a few meters wide, Earth itself is a complete system, with an atmosphere, water, a magnetic field, and natural cycles that sustain life on a planetary scale. This difference does not need to be interpreted emotionally. It can be observed directly, through the window of a spacecraft returning home. As Orion continues its journey, Earth gradually grows larger in view. Details become clearer. The outlines of continents, weather systems, and reflected light from the oceans become easier to distinguish. At the same time, onboard systems transition into re-entry preparation. Trajectory calculations are updated. Parameters are checked again. Everything moves toward a specific objective, guiding the spacecraft back into Earth's atmosphere at the correct angle and velocity. But before that phase begins, there is a brief moment where two things exist simultaneously. Connection is restored, and the image of Earth returns to view. And that is the point where the journey is no longer about how far we have gone, but about how we return. When following Artemis II, one of the most common questions that arises is not about complex engineering, but something much more direct. If humans have returned close to the Moon after more than 50 years, why didn't they land? The answer does not lie in a lack of capability, but in how space missions are designed in stages. Artemis II was not built as a landing mission. From the beginning, its objective was to test the entire human-rated flight system in deep space conditions, including the Space Launch System, the Orion capsule, life support systems, and the crew's ability to operate in an environment beyond Earth orbit. Looking at the overall structure of the Artemis program, each mission serves as a separate validation step. Artemis I was an uncrewed test flight focused on evaluating Orion's ability to travel around the Moon and return safely. Artemis II is the next phase, introducing humans into that system to test elements that can only be fully assessed with a crew on board. Landing, according to the plan, is reserved for Artemis III. This is not a delay, but a risk management approach. A lunar landing mission requires more than simply reaching lunar orbit. It demands an entirely separate system, a landing vehicle, descent procedures, surface operations, and the capability to return to orbit after completing the mission. Each of these components introduces its own technical requirements and potential points of failure. In Artemis II, these elements are not yet deployed. There is no lander on board, no descent procedures are executed. Instead, the mission focuses on confirming that humans can travel to the moon, operate in deep space, and return safely using the current system. Another key factor is the design of Orion itself. The Orion capsule is not a vehicle capable of landing directly on the moon's surface. It is optimized for spaceflight and Earth reentry. To perform a landing, Orion must be paired with a separate vehicle, commonly referred to as the Human Landing System, HLS, which is being developed in parallel within the Artemis program. This creates a sequence of steps that must be validated before a complete landing mission can be carried out. First, Orion must demonstrate that it can reliably transport a crew to lunar orbit. Next, life support and operational systems must be confirmed to function under real conditions with humans on board. Then, the landing system must be integrated and tested, including docking in lunar orbit, descent to the surface, and return to orbit. Artemis II exists at the early stage of this sequence. Skipping these validation steps and proceeding directly to a landing would significantly increase risk. In the space environment, where external intervention is nearly impossible in real time, minimizing risk through mission design becomes essential. One notable point is that although Artemis II does not land, its trajectory still brings the spacecraft closer to the moon than many previous missions. This allows for environmental data collection, real condition system testing, and evaluation of how different components perform together with a crew on board. From a technical perspective, this is a necessary progression. From an observer's perspective, it may feel like an incomplete step. This difference reflects two ways of viewing the same mission. One perspective expects that returning to the moon means repeating past achievements, including landing. The other reflects a modern approach, where each stage is validated independently to ensure system reliability before moving forward. This also relates to another reality. Today's space technology is not a direct continuation of Apollo-era systems. While the underlying principles may be similar, modern systems are designed under different standards, with greater emphasis on safety, reliability, and scalability for long-duration missions. This means that even though humans have landed on the moon before, doing so again with new systems requires validation from the beginning. In this context, Artemis II serves as a bridge. It connects proven capabilities from the past with the requirements of future missions, not only for returning to the moon, but also for preparing journeys farther into space, where distance, time, and autonomy will be significantly greater. And within this sequence, not landing is not a limitation. It is an intentional choice. A choice based on the understanding that in space, every step forward must be built on a verified foundation. Not to slow progress, but to ensure that when we go farther, we can still come back. And that is what Artemis II is designed to prove. As Orion leaves the moon's direct sphere of influence and begins its return journey, the focus of the mission shifts to a decisive phase. If traveling to the moon is a problem of trajectory and energy, returning to Earth becomes a problem of control and physical limits under extreme conditions. At this point, the spacecraft no longer needs to maintain orbit around any celestial body. Instead, it must adjust its path to intersect Earth's atmosphere at a precise angle and velocity. The margin for error is extremely small. If the reentry angle is too shallow, the spacecraft may skip off the atmosphere and return to space. If it is too steep, the heat and forces generated will exceed the capacity of the heat shield. Orion's velocity at the start of reentry is approximately 25,000 miles per hour, equivalent to more than 11 kilometers per second. At this speed, the challenge is no longer about moving fast or slow, but about how to dissipate energy. The spacecraft's entire kinetic energy must be converted into heat within a very short period of time. As Orion enters the upper layers of the atmosphere, the air in front of it is compressed at extremely high pressure. This compression rapidly increases the temperature of the air to several thousand degrees. This is not caused by friction in the traditional sense, but by the rapid compression of gas molecules. The result is the formation of a plasma layer surrounding the spacecraft. The temperature at the surface of the heat shield can exceed 5,000 degrees Fahrenheit, or roughly 2,700 degrees Celsius. At these levels, most conventional materials would fail immediately. However, Orion is equipped with an ablative heat shield made of AvCoat, designed to absorb and remove heat through controlled material degradation. The key point is that the heat shield does not resist heat by maintaining its original structure. Instead, it sacrifices part of its material to carry heat away from the underlying structure. As the outer layer is exposed to extreme temperatures, it breaks down and carries energy away, helping to keep the cabin temperature within safe limits. Throughout this process, the interior of Orion remains at approximately 20 to 25 degrees Celsius. The temperature difference between the exterior and interior can reach thousands of degrees, but it is managed through material design and structural engineering. Another important factor is acceleration. During reentry, Orion experiences increasing g-forces as it interacts with the atmosphere. These forces can reach approximately 3.5 to nearly 4 g, depending on the trajectory. This means the crew experiences forces nearly 4 times their normal body weight. Maintaining awareness and operational capability under these conditions is part of their training. In addition to heat and acceleration, there is another familiar factor from previous missions: plasma blackout. The plasma layer surrounding the spacecraft not only generates extreme heat, but also blocks all radio signals. For several minutes, Orion once again loses communication with Earth. However, unlike the blackout behind the Moon, this phase occurs under significantly higher energy and physical stress. Everything happens faster, and the variables are greater. As the spacecraft descends deeper into the atmosphere, its velocity gradually decreases. Energy is dissipated through interaction with the air. After the peak heating phase, the surrounding environment becomes more stable. The plasma dissipates and communication is restored. At this point, Orion enters the final phase of reentry: deceleration using parachutes. The parachute system is not a single deployment, but a sequence of precisely timed stages. First, smaller parachutes are deployed to stabilize the spacecraft and prepare for the next phase. Then, the main parachutes, with large diameters, are deployed to reduce the capsule's velocity to a safe level for ocean splashdown. Before parachute deployment, Orion's speed is still in the range of hundreds of miles per hour. Once the system is fully deployed, the velocity decreases to approximately 17 miles per hour at the moment it contacts the ocean surface. The entire process takes place over tens of minutes, but each stage has a specific role and cannot be omitted. One notable point is that although re-entry has been performed many times in history, returning from lunar orbit presents unique challenges. The higher velocity, greater energy, and tighter margins for error distinguish it from re-entry from low Earth orbit. This makes the return phase one of the most critical parts of the entire mission. If re-entry proceeds as designed, the result appears simple from the outside. The capsule lands safely, the crew is recovered, the mission is considered successful. But that simplicity is the result of a complex sequence of physical processes operating within narrow limits. And viewed from this perspective, there is an important point to recognize. Reaching the Moon is a significant achievement, but returning is what confirms that the entire system truly works. In Artemis II, re-entry is not just the final step of the journey, it is the integrated test of everything that came before. The trajectory must be precise. The systems must remain stable. The crew must maintain operational capability. And the heat shield must perform exactly as designed. Because during those minutes between the spacecraft and the external environment, there is little more than a single layer of protection. And everything depends on that layer working exactly as intended. When Orion splashes down in the Pacific Ocean, and recovery teams approach the capsule, from an external perspective, the Artemis II mission can be considered complete. The crew is safe. The capsule is stable. All major phases of the journey have unfolded as planned. But in space missions, especially those designed to test systems, the moment of completion does not lie in the landing itself. It lies in what is collected and how that data is understood. Immediately after the capsule is secured on the recovery vessel, the inspection process begins. This is not a procedural formality. Every surface, every structure, every system is examined in detail to determine how it performed throughout the mission. One of the most closely examined components is the heat shield. As noted in earlier missions, Artemis I revealed non-uniform behavior in the ablative performance of Avcoat, including cracking and uneven material loss in several areas. This led to design adjustments and, importantly, changes to the reentry profile of Artemis II, aimed at reducing internal pressure buildup within the material. After Artemis II, the heat shield is not only inspected at a general level, but also analyzed in detail. Engineers look for indicators such as the depth of material erosion, fracture patterns, thermal distribution, and especially any areas that deviate from predicted models. The goal is not simply to confirm that the system worked, but to understand precisely how it performed under real conditions with a human crew on board. If the results align with predictions, this strengthens confidence in the current design. If deviations are observed, even minor ones, they are analyzed to determine their cause and assess their impact on future missions. Beyond the heat shield, the entire life support system is also evaluated. Data related to cabin pressure, oxygen and carbon dioxide levels, temperature, and humidity are compared against expected values. Any differences are recorded, not for immediate fault finding, but to better understand system behavior under real operational conditions. Radiation sensors onboard Orion provide another critical data set. These measurements help determine the level of exposure experienced by the crew throughout the mission, particularly while outside Earth's magnetosphere and during passage behind the Moon. This information has direct implications for long-duration missions where exposure time will be significantly greater. Another essential source of data comes from the crew themselves. Throughout the mission, astronauts record personal observations, physiological responses, and operational experiences. These insights cannot always be captured by sensors, but they provide an important perspective for evaluating how systems function in practice. For example, how the crew experienced blackout periods, how easily they were able to interpret system data without support from Earth, and how their bodies responded to high G-forces during re-entry. All of these are documented and included in the analysis. When all of this data is combined, a clearer picture of the mission begins to emerge. Artemis II is not a mission of exploration in the traditional sense. It does not return samples from the lunar surface. It does not establish a base or conduct long-term experiments on another celestial body. Its value lies in confirming that humans can operate in deep space using the current system. From this perspective, the result of Artemis II is not simply success or failure. It is a collection of answers to the questions that were defined before the mission began. Can Orion maintain a stable living environment throughout the mission? Can the navigation system preserve accuracy without continuous intervention from Earth? Can the heat shield perform as designed under real re-entry conditions? And more importantly, can all of these systems function together in a crewed mission? Initial results from Artemis II indicate that most primary objectives have been achieved. The capsule landed within the expected range. Critical systems remained stable. The crew completed the mission without major incidents. But within the broader context of the Artemis program, this is not the end. It is a transition. The data collected from Artemis II will be used to refine designs, adjust procedures, and prepare for subsequent missions, particularly Artemis III, where the objective shifts from orbiting the Moon to landing on its surface. This means that even if Artemis II is considered a success, the real work continues. In space missions, each flight is not just a journey, but a part of a longer process. A process in which each step provides information to improve the next. And in this case, Artemis II has delivered something essential. Not a new discovery about the moon, but a confirmation of human capability when moving beyond Earth. And that becomes the foundation for what comes next. When all the data from Artemis II is analyzed and placed within the broader context of the mission, one thing becomes clear. What the spacecraft experienced behind the moon was not an extraordinary event in a technical sense. Everything occurred as expected. The trajectory was precise. The systems operated normally. The crew followed procedures as planned. But from another perspective, the fact that everything remained normal in such an environment is what stands out. During the nearly 40 minutes of lost communication, Orion encountered no major issues, no critical warnings, no emergency situations requiring intervention. All systems continued to function as designed. And when the signal returned, the mission proceeded without significant interruption. This suggests that, technically, we have reached a certain level of control over the deep space environment, at least within the scope of a short-duration mission. But at the same time, it highlights another limitation. That control is not absolute. Throughout the mission, there are factors that humans can predict and model with high accuracy: trajectory, velocity, temperature, pressure. But there are also factors that we can only measure and adapt to, not fully eliminate, such as radiation, signal delay, and separation from Earth-based support systems. The silence behind the moon is a clear expression of that limitation, not because we lack the technology to maintain communication, but because the environment does not allow it. And when the environment imposes limits, technology must adapt to those limits, rather than attempt to override them completely. This has important implications for how we approach future space missions. Artemis II operates relatively close to Earth. The communication blackout lasts only tens of minutes. Signal delay, when present, is just over 1 second. But as distance increases, these conditions change. In missions to Mars, one-way communication delays can range from 4 to over 20 minutes, depending on the relative positions of the planets. This makes real-time communication nearly impossible. Critical decisions will need to be made entirely by the crew, based on the information available at that moment. In this context, the 40-minute blackout of Artemis II can be seen as a small-scale model, not in terms of duration, but in principle. It demonstrates that there are phases of a mission where humans must operate without direct support from Earth. And during those phases, system reliability and human capability become the determining factors. Another important aspect is how this silence is perceived. In technical reports, blackout is described as a normal part of the mission. It is calculated, predicted, and integrated into operational planning. But for observers, the silence often carries a different meaning. It creates a gap in information, and within that gap, human perception tends to fill in assumptions. This is not a negative reaction. It is a natural characteristic of how humans process incomplete information. When data is absent, we imagine what might be happening. In the case of Artemis II, everything proceeded according to plan. But that could only be confirmed after communication was restored. Before that moment, there was no way to know for certain. This leads to an important understanding. Silence is not a sign of failure, but it also provides no guarantees. It is simply the state in which information is unavailable. And in space missions, this state will appear repeatedly, especially as distance from Earth increases. From a systems perspective, Artemis II demonstrates that humans can operate under such conditions for short periods. But from a long-term perspective, it also shows that expanding human presence in space will require accepting periods without direct supervision. This is not a limitation that needs to be removed. It is a characteristic of the environment. And understanding that characteristic is an essential part of preparing for future missions. When considering all factors, trajectory, radiation environment, life support systems, and the psychological state of the crew, Artemis II is not just a test flight. It is a confirmation that humans can operate beyond continuous connection with Earth for a certain period of time. But it also reinforces that connection still matters. Not because we cannot function without it, but because it provides a layer of information and support that, when absent, makes the environment fundamentally different. The silence behind the moon, in this context, is not something to fear. It is part of reality. A reality that any mission beyond Earth orbit must face. And seen this way, Artemis II did not only bring back data, it brought back a confirmation that as humans travel farther, there will be moments when we must accept that answers are not always immediate. Tonight, as you rest in a familiar place, with air you do not have to think about, and light you can turn on at any moment, you may remember that, on the far side of the moon, there was once a silence, with no sound, no signal, and nothing to rely on except the human presence itself. Artemis II has returned, but that silence still remains there. And perhaps what matters is not how far we can go, but how well we understand where we are. Let your mind slow down, like the trajectory of a spacecraft drifting through quiet space. And if tonight you are still awake, then at least you are not completely alone.